All right, 1.3, here we go. We're going to learn how to do some linear regression, and some of this we'll need the calculator for. So first of all, what I want to show you is just down here at the bottom what we mean by a linear model. And let's see, the variables x and y are linear related, then they have the form y equals mx plus b. We're going to get into this a little bit, but the first thing I want to show you is what we mean by a rate of change, and that's what that m is that's given a rate of change, and that's given what we call the slope of the line, and we've already learned that, and b is the y-intercept. Okay, so we've learned that and talked about that a little bit. Now what I'm going to do is just show you how to identify a linear relationship from a set of points. All right, so here's kind of an example of this. You have price of a taxi cab ride. This is the number of miles. This is the cost. Okay, so here's kind of what happens. Here's how I know this is linear. And that's because if this goes up 1, then this appears to go up by 30 cents. And that will continue with that progression here on out. That goes up 1. This goes up again 30 cents. And if you look down the list on that, every time that goes up 1, that goes up 30 cents. Okay, that's what a linear relationship looks like. And if you plotted these points, like you have the point 0, 1, 1, $1.30, 2, $1.60, if you just plot those points, it's going to make a straight line. So that's how you identify linear relationship. All right, so let me just show you this, and then I'll let you make sure that you got this down. So this one right here, if you look at this one is going to go up 2, and this is going to go up 6. Now we need to make sure it does the same thing throughout the table. So again, from 2 to 4, that's up 2. Again, that's up 6. Okay, same thing here, up 2, up 6. So that is linear. Okay, and that's how you can tell from a set of data if it has that characteristic to it. Okay, if you look at this one, let's see what happens on this one. This one goes up 1, this goes up 3, and then we would have to see if that same relationship existed throughout. Okay, now we go up 1, go up 5. Okay, that's good enough. It's not linear. Okay, so you'll notice on this one it has a totally different type of relationship. This one's going to go up in a pattern. It goes up 7, then it goes up 9, then it goes up by 11. Okay, that's not linear. What it actually is it's actually quadratic. So what happens is on this one, y is equal to x to the second. All right, so if you just do 1 to the second, you get 1, 2 to the second's 4, 3 to the second's 9, 4 to the second 16, and so forth. So it's not linear. It wouldn't have that form y equals mx plus b. Okay? All right. So we're looking for a constant rate of change every time that we're looking for a linear function then. All right, so what I want you to do is pause my video and just look at these and write linear or nonlinear. All right, so this is what you should have came up with. This first one's nonlinear. You can see that that's going up 1, but those are going down by different amounts. The second one's linear. X goes up 1, Y goes up 1. That's linear. C is also linear. X goes up the same amount 1, so does the Y. All right, so those are 2 linear functions on that. All right, so now we're going to talk about the slope as a rate of change. All right, and that just means the rate of change is constant. It's always the same. So if we calculate the slope using any 2 points on the line, it'll always be the same. So what we're looking for, slope is you have 2 points. I'm just going to have you kind of fill out this point right here. We'll just give that a general name, x1, y1. This point right here, we'll give this a general name, x2, y2. Right, and what happens is it's just a ratio of rise over run. This part right here is called the rise. That's how far up you go from point to point. And then this part right here is the change in the x coordinate. So that's called the run. Okay, so what happens is we say delta y, that's the change in y. All we do when we do the change in y is we just subtract these two values. That's how high up that point is. That's how high up that point is. So we do y2 minus y1. That's the distance between that y value and that y value there. Okay, then what we do is we do the run, which is the distance between the x's. So I do x2 minus x1 like that, and that gives you what's called the slope formula, right? Well, it's good to know where that comes from. And since at any 2 points on this line, that rate of change would always be the same. So if you picked a point here and a point there and drew a triangle on that, the ratio of the rise to run would be the same. And it always would, no matter where you are on that line. Okay, so I'll do a couple of applications here of a linear model, what we call linear model. So this says, a physician published the following estimate of the ideal body weight of a woman, and it says it's 49 kilograms to begin with. That's kind of the beginning weight. And then you got this condition that as you're over 5 feet, you gain 1.7 kilograms for every inch. So that's a linear model. So the way that this would go like this, we're going to find a linear model of the estimate of the ideal weight of a woman. W is the ideal body weight in kilograms, and H is the height over 5 feet. Okay, so first of all, it's going to go like this. All right, so to begin, all right, so since this is a linear model, it's going to have this kind of structure to it, but the variable is going to be different. That's going to be your weight. This is going to be kind of like your rate of change, which is given, and then x is going to be the height, and then we have this plus b right here. All right, well, what happens in this particular problem is it goes like this. The weight, this is the variable part right here. All right, so you start at 49 and you add 1.7 kilograms for every inch. Okay, so what you would do on this is you would say 1.7 times h plus 49 like that. All right. Now what would happen is that would be a linear function. All right. And so that would be what your linear function is based on that information. You start at 49, so you can think of that as a y-intercept, and you can think of that 1.7 as the slope. Okay. All right, so that's kind of how that works out then. So interpret the slope. Well, the slope is equal to 1.7. Now remember what that is that's a body weight. Okay, that's kilograms. If we put that over 1, what we're really doing on this is we're doing the change in the weight over the change in the height. So what it's saying is the slope is a measurement of you grow 1.7 kilograms every time you grow an inch. So that's a good way to think of the slope, is to think of it as delta W over delta H like this. Okay, so if you interpret the slope, it just means each inch you gain 1.7 kilograms. So that would be a way to interpret the meaning of that. Okay, now this next problem says if a woman's 5 foot 4 inches tall, what does the model predict her weight to be? So first of all, what you'd end up having is if she's 5 foot, then we know she weighs 49 kilograms. But we have this extra 4 inches that we have to figure out. Okay, so what we actually do in this is the H is not going to be 5 foot 4. H is going to be 4 inches. Because remember, it's the inches past 5 foot. So you'd work this out like this. Your model that we built is W is 1.7H plus 49. So that's 1.7 times 4 plus 49 like that. Okay, now we can use a calculator to assist us with this. So if we do 1.7 times 4, That just means that 4 inches, she gained 6.8 kilograms. Okay, so that's really the 6.8 kilograms. It's the 49 kilograms, and then add those two together. And then we'll get this. So the final weight on that would be 55.8 kilograms would be her weight then. All right. Okay, so that's how you put that together. All right, got it? Okay. All right, now this next question is asking something a little bit different. It's saying if the woman weighs 60 kilograms, so what that would be is that would be the variable W would be 60 kilograms. Then you would say, what does the model predict that her height will be? Well, let's write down the model and think about what we would do here. Now, you have an equation that's got two variables in it. We know the weight is 60. But what we don't know is the height, so we're going to solve an equation to solve this problem then. So all we're going to end up doing is just doing 60, and that's kilograms, equals 1.7h plus 49. All right, so that's just kind of a standard linear equation. We can move the 49 the other side or subtract from both sides. And if you did that, you would have 60 minus 49 equals 1.7h. 60 minus 49 is 11. Okay, then what we do is divide by 1.7. And then we get our calculator out and get what that height is, and just round it off if we need to. So that would be this. So that would be 11 divided by 1.7. Okay, so we're just going to round that off. So it's about 6.5 inches is what h is. Okay, so the woman's 6.5 inches, right? No. Okay, how tall is she? She's 5'6.5". Okay, that's what it is. Remember, the height is past the 5 feet. Okay, so that's how that would go. All right, think about your answer. Okay, she's not 6 inches. She's not a Barbie doll. Okay, all right. That takes care of that then. Let's move on to the next thing here. All right, so this one says the table below lists U.S. fossil fuel percentage as a total percentage of total energy production for several years. So these are years. These are the production amount of energy that's fossil fuels. Okay, and this is a pattern going down as we get into more and more renewable energy sources. We'll see this going down. That's a goal. At least I hope it's a goal. All right, so a linear regression model for this data is this. Now, this is a mathematical model that's already given. Unlike the last problem where we figured that out, this is already given. X represents the years since 1965. So actually what would happen is this would be X equals 0. Then this would be 5 years later, 10, 15, 20, 25, and 30. So 30 years later would be that. All right, so I graduated high school in 1981. This makes me feel old. So that's 30, okay, like that. So the energy production changed after 30 years. So what we're going to do is we're going to do a couple of statistical things that we do. We can do a scatter plot. Anytime I ask you to do a scatter plot, what you're essentially doing is just plotting your data and looking at your data points on here primarily. So when you do a scatter plot, all you really usually got to do is just do a positive axis for X and a positive axis for Y. And then you need to label everything and scale everything. So this would be, and it's important if I ask you to draw a scatter plot to label stuff. Students a lot of times don't label anything, and then your graph is meaningless. So this is years since 1985. So we're not going to go like 1985, 1990, and so forth. We're just going to go, we'd be logical to go by fives and just label that like this: 5, 10, 15, 20, 25, and 30, like that. And then we have a percentage. Okay, the percentage, and let me show you a little trick you can do on this. The lowest percentage that I see is 78. The highest is 85. So no, you don't have to go 5, 10, 15, 20. I see students do it all the time and then have this little tiny bit of data there. A little trick you can do, and this is a valid thing to do, is you can put this little kind of squiggly line there, and then you can start this. Probably a logical place to start this to me would be like 75. Then you could go 76, 77, 78, 78, 6, 7, 8, 9, and then there's 80. 1, 2, 3, 4, 5, kind of like that. Okay. All right, that's the logical way to do that. You can use that little squiggly line. You can't just start like this. I don't ever want you to just start like that. If you're going to do this, use this little notational symbol right there to do that. So I'm okay with you doing that. Then we just plot the points. So see, this point right here is 1985. It's really the point 085. So we just put a dot there. The next point is 583, and so forth. So we go to 5, we go up to 83, then we go to 10, and that's at 81. And then we go to 2000, so that would be right at 80. And then we go to 2005, which would be 79. And then the next data point is 78. And then the 30 years later, you're back up to 80. Okay, now that's not a perfect line, but what this thing is here, we're going to learn how to use our calculator to get what we call a line of best fit. That's called a linear regression. So we're going to call that a line of best fit. So using statistical methods, you can find a line that best fits that data, kind of minimizes the errors. So in reality, when you're modeling data in the real world, it's not perfect, but you can use mathematical methodology to make the estimate very tight and minimize the errors. That's what we mean by linear regression. All right, so what we're going to do is we're going to look at the slope on this, and you don't have to calculate the slope because it's already built into our equation. So our equation is y equals negative 0.19x plus 83.75. Now, sometimes students have trouble doing this, and that tells me they don't understand what the data is showing. See, x in this is years past 1985. Y is the percentage of the production of fossil fuels. So this number right here is your slope. If you're going to tell me what the meaning of a slope is, you have to understand the formula for a slope. So remember what it is it's delta y over delta x. It's the change in y over the change of x. So what does that really mean? It means the change in production, and that again was what? Fossil fuel production. I'm going to abbreviate that kind of like that. So it's the change in fossil fuel production over the change in time, okay, the change in years. So really what you would have on this, if you model this now, you got negative 0.19 over 1. So this is the percentage. This is the year. So if you were going to write a good interpretation of this, don't say rise over run. That doesn't tell me anything. It tells me nothing. Here's the way I'm going to have you write this. I'm just going to kind of write this over at the side here. What we would say is each year fossil fuel production. And what happens? Does it go up or does it go down? That's a negative, so it's going down. So we'd say fossil fuel production, and I'm going to say decreases by 0.19% per year past 1985. Okay, that's the way that you would interpret that. is basically it's a rise over run, but the rise is giving fossil fuel production and the run is giving change in years. So that is what that interpretation means. You want to know what these things mean, okay? So what we're going to do is use the model to predict the fossil fuel production in 2025. Okay, well, again, we write down our regression equation. Y equals negative 0.19x plus 83.75 and 2025. Now, we're not going to plug 2025 in. Okay, now remember, if you look at your data here, X is the year, Y is the fossil fuel production. Okay, well, you got to figure out how many years this is. So if you do 2025 minus 1985, and that'll tell you how many years apart that is then. Okay, hopefully I got that. Did I make a mistake on this earlier? No, I'm okay. 2025, so that's going to be 40 years later is what that is. Okay, so we're okay. So it just means 40 years later is the year 2025. So we're going to make this prediction. We should see this trend going down. So what we do is just do Y equals negative 0.19 times 40 plus 83.75. Okay, then we can get the calculator out and we can calculate that out. Okay, so this would go like this. I'm just going to put it in. So I've got negative 0.19 times 40 and then plus 83.75. Whoops. Okay, and then this should give us the amount then. All right, so I got that put in correctly. So that's about 76.15% is what the answer to that would be then. Okay, so you're using your mathematical model to make predictions in the future. That's what we use this kind of stuff for. Okay, and then the next thing it says, use the model to estimate the first year for which fossil fuel production is less than 70% of total energy production. Okay, so to process this, again, let's just write down the equation and kind of think about what that linear model is doing. Okay, well, we just figured out, see, this part right here is the fossil fuel production. So we're going to find when does this get down to 70%. So really all we got to do is just plug in 70 there. Like that, and then we'll have an equation to solve. And that will give you the years past 1985 when that happens. Okay, so we just do 70 equals negative 0.19x plus 83.75. You could also do this with an inequality, but we're just trying to find the first year this happened, so this is good enough. All right, so what I'm going to do is just subtract from both sides. I'll end up having 70 minus 83.75 equals negative 0.19x. Okay, I can take my calculator and work this out. So I do 70 minus 83.75. So that's going to be equal to negative 13.75 equals negative 0.119x. Okay, like that. And I divide by this value. Okay, and that will give me this. Okay, so the negatives divide out, so I'm just going to put in 13.25, or hold on, was that a 7.5? Yeah, that's 13.75. Oh, come on. Have to touch my screen on this to get this to work right. 13.75 divided by 0.19 is going to give this. All right, now that's something that we just round off, so let's just round this up to about 72. Now, that's the years past 1985. So what we need to do is we need to do 1985 plus 72. and then that'll give us what we're looking for. So 1985 plus 72 years later, about 2057. Okay. Now, I sincerely hope that by the year 2057, I probably won't be around by then, but I might, that we are down to very little fossil fuel production. That's my opinion. We need to be less than 70%. All right, so in reality, our goal is probably not going to follow a line. Our goal is more or less going to follow some sort of a curve that's nonlinear. All right, so using that model, though, that's how long it would take to get that production level down that to 70%, which is not good in my opinion. Okay, let's move on. And now what we're going to do is we finish up mostly on this with learning how to use our calculator. So we're going to find linear regression models using our calculator. So we're going to find it using a statistical method known as linear regression. So here's just a couple of examples on this. This would be like the temperature in degrees Celsius and the sales. Well, you might not think that follows a linear path, but it might. The warmer the temperature is, maybe the more people go shopping. Okay, so that could be a linear model. This one says the age and the average emails per day. Well, that kind of makes sense. Younger people may get more emails than older people. Older people don't even know what the internet is. That 72-year-old there can't even check their own email, maybe. So, I mean, that could be linear. I don't know. All right. So let me show you kind of how this goes. This is the way that you're going to do this. And primarily, what I'm going to do is I'm going to just take a snapshot of this. And when we go to the next page, we'll be able to review this and use this. Okay, so I'm going to go ahead and just take a snapshot, and this will show you how to the steps that you need to do on a calculator. And this is a fairly easy thing to do. It really is. All right, so I'm going to demonstrate how to use technology. If you don't have technology, this problem is a nightmare. I mean, there's nobody in the modern world anymore that does linear regression by hand because it's just too complicated. All right, it's not that it's hard, but it's just arithmetic, like that would take you forever to get this done. So nobody does it any other way in the modern world other than use technology. So this is climate data. This is giving you the years. This is giving you the average annual temperature in Fahrenheit, and this is the annual precipitation. So a lot of times if we're doing scientific analysis, we do data analysis and we try to find mathematical relations. So the first thing we're going to do is we're going to do a scatter plot. And again, when you do a scatter plot, all you really usually need is just the positive x-axis and the positive y-axis. Okay, so it's going to go like this. All right. All right, now what we're going to do is we're looking at the average temperature. So we're not looking at this stuff. We're just looking at this data right here. We're not really paying any attention to that. So we need to figure out how to scale this. Okay, we can do, I'm going to call X years past. It's a good idea to just say years past 1965. Okay, it's better to do that than to actually start your graph at 1965. And by doing that, we're just going to go every 10 years is how this is going. So we'll just go like 10, 20, 30, 40, 50, and then 60. So 1965, 60 years later is the year 2015. And then this stuff right here, again, you don't go 5, 10, 15, 20. Don't do that. That's ridiculous. Okay, do this. Like I did on that last example, learn to do that little squiggly line. Find the lowest data. The lowest data I see is 51.3. The highest data I see is 54.4. And use that to kind of decide how you're going to scale this. All right, so I'm going to zoom on this kind of big on here so I can see what I'm doing. So let's see, we probably want to start at like 51. And then we could go like to 52, 53. Try to draw big when you do this stuff. And then 55, okay, like that. And we can estimate where this goes. So we can put like, the halfway marks in there like that if you want to. Now all we're doing is just plotting points. So the first one has a data item of 51.69, so just do your best to estimate where that is. The second data item is 51.5, so it's a little lower. And then the next one at 20 years later is 51.3, so it's a tad bit lower. 30 years, you shoot up to 52.65. So we're beginning to move up here, looks like. 40 years, you're up to 53.64. Did I miss something? I'm okay. All right. So that's just one more. I think I went out too far on my x-axis is all I did. Yeah, okay. So then the last data item is 50 years later, 54.4. Okay, so if you look at your data, it sort of looks like it might do a line. You could make a line a best fit there. The trend looks like it's moving upwards. Okay. So what we're going to do is use the TI calculator to find a linear regression equation. So I'm going to show you how to do that. I'm going to get my calculator here and display it. You want to get your calculator out and you want to do this with me. You got to have a TI calculator to do this. So you have to have one for this class. So we're going to follow this like this. So the first thing you're going to do is press the Stat button, which is here, and you want to highlight Edit, then press Enter, and you want to make sure that your lists are clear. So if you have some stuff in a list, what you always want to do is just go up to that L1, press Clear, and press Enter. All right, and we'll go like that. Now, if you don't have L1 and L2, if you don't have that, you can reset your stat editor this way. You can go Stat and then Set Up Editor, and that should take it back to a default setting if you do that then. All right, so let's start over again. We go Stat, we go Edit, everything's cool. Now we're going to, this goes in X. Now we're not going to start with 1965, we're going to start with 0. Okay, then we're going to go 10, kind of like we did on our scatter plot, then 20, then 30, and so forth. Then 40, you got to press Enter each time you do that, so it goes like that. Then you can move over with your right cursor key, then put in your other data. So the first one is 51.69, 51.5, 51.3. Don't have to put the 3.0 in there, that's not necessary. 52.65 and 53.64. And the last one is 54.4. So you want to make sure your data is incorrect when you do that then. All right, so that you'll have that as your data. That needs to be put in like that. Then what we do is we got our data in, so we're going to go all the way down to the bottom here. All right, so we start over again. We go Stat, move to Calc, go down to option 3, which is a linear regression. That may be different for different calculators. This one may be different. There's 2 linear regressions, so I guess on my calculator it's option 4. You'll see that on there. Do that one. Okay, usually it'll look like this. X is an L1. That should come up default. Don't worry about anything else. Just go down to Calculate, press Enter, and there you have it. Okay, so what you've got on your calculator, what's coming out, is you have this equation. You have y equals, and see, A is your slope, and I'm just going to round that to like 4 decimals and put 0.0609x. I'll do the same thing for the y-intercept, just use 4 decimals, 51.0071. So what that's doing is that is given that line of best fit for you. Okay, so what I'm going to show you how to do is how to set this up kind of on your calculator next here, and then we're going to do a prediction on here. So the next thing I want to show you how to do is how to do this scatter plot on your calculator. So the first thing we got to do is we got to press our window button, and we need to get the window set up the same way we did here. So let's go 0 to 60 by a scale of 10. Okay, that's what we're doing there. Is go x-axis going 0 to 60 by 10. The y, now what you can do on this is you can go ahead and start it anywhere you want to. Let's just start it at 51 like we did. And then we're going to take that all the way up to 55. And then we can scale by 1 if you want to, or we can scale by, let's scale by 1 like that. Okay, now you got to go to y equals. If you have something in there, you clear it. You got to highlight the plot. So get that blinking and press enter. Now if you press graph, then it'll have your data in there. So it's similar to what we have there. Okay. All right. So again, you do the window. I can slide these things over so you can refer to these things if you're studying this. So that's the window I did. And then the key thing is you had to have that plotted. Now what we're going to do is we're going to put in this regression equation. So you want to press y equals and then put this in. So 0.0609 times x plus 51.0071. Now type graph. And what that'll do is that gives what we call the line of best fit. You can tell that that model does a good job of estimating that data. All right, so that's kind of what we have there. So we got that. So that's the idea. Okay. I'll show you a couple of ways to solve the next part of the problem. The next part says, what is the temperature going to be in 2025? Well, 2025 would be, if you count this out, 0, 10, 20, 30, 40, 50, 60. So this would be when x is equal to 60 years. So we just do y equals 0.0609 times 60 plus 51.0071. And we can do that on a clear screen. Anytime you want to get to a clear screen on the calculator, there's a quit button. So you go second quit and you put it in. So you go 0.0609 times 60 plus 51.0071. Okay, so it gives you this. That would be 50.3725. So the average temperature would be about 50.37 degrees Fahrenheit. And that would be the solution. Okay. All right, so that's how that goes. All right, so that's the problem dealing with technology. Okay, I'm going to move on to the next page here. And on this next page, I'm going to let you all do this yourself. So what I'm going to actually do, I'm going to make a copy of this. So that way, if you want to do this, you can just look at the screen, you can pause, and then you can look at the steps if you need to do the steps on that. Okay, so I'm going to go ahead and pause, let you do that, and then come back and check when you're done. Okay, so I'll let you go ahead and check and kind of see what you have here. So here's the scatter plot. You want to have something that kind of looks like that. The data doesn't have to be perfect. You just do your best to estimate that. When I rounded my regression equation, I have this. This is how I put my data in. I started with 0 and went up to 24, and then put in the time and seconds there. And that's what I got. When I put this in the graphing calculator, that's how the data should have went. Okay, now I didn't rechange my window. I probably should have done that, but it worked okay just using the same thing from the previous problem. So let me go through and do this again. You go 0 to 24, by a scale of 4. This is a better way to do this, is like that. And then we can start from 52 and then go up to 55. So probably a little bit better to do it that way. Mainly on that, I just want you to see that your linear model looks correct. So it should look kind of like that, all right? Okay, and then the next one, the year 2020 would be 28 years later, so you do that to get your answer. All right, so that's it. Hopefully you did okay. Let me know if you have any questions.